Hi, I'm Duane Bailey, and I'm from Williams College, and this is a talk I sort of informally developed research with a bunch of my students who are now ruling their lives at places like Facebook. I have a little problem that was popularized by Ben Chafin and Neil Sloan, and you can do this while you're waiting for your pizza order to come in. What you do is you write down a small sequence of small integers, and you try to compute what the maximum suffix repeat count is for that sequence. So for example, if you've got 1, 2, 3, 3 repeats once, 2, 3 repeats once, 1, 2, 3 repeats once. So we're going to call this the curl of that sequence, and the curl is 1. Now from now on, I'm not going to use any more commas. I wore out the comma in my keyboard, so we're going to just run the numbers together. So 666, 6 repeats 3 times, 6, 6 repeats once, 6, 6, 6 repeats once. So the curl of this, the maximum repeat count, is 3. Now, it turns out that 6s are not really important. The whole problem can be really dealt with by just thinking about 2s and 3s. So here's some 2s and 3s, 2, 2, 3, 2, 3. And this requires a little bit more work. The suffix 3 repeats once. 23 repeats twice, so the curl of this is 2. Now, you might think, if you want to prove things inductively about this, you might want to add some more digits on at the beginning of the sequence. And so we'll do that. And so 2, 3, 2, 2, 2, 3, 2, 3. The curl of this remains 2. So the induction is not always going to be helped by just appending more digits. So the interesting thing is when you take this curl and you make it adjacent to the sequence, and then you just start letting it rip, you just compute the curl iteratively until you get this entire tail. And you'll notice at the very end, it ends up with a curl of just 1. And so that's really kind of interesting. And in fact, we don't know of any sequences that just sort of diverge. So the conjecture is that all the tails of these curling sequences are finite. I am not going to be able to help you with that problem today, but I wanted to show you a couple of tools for taking a look at this problem. So Chafin and others took a look at the longest tail for any starting sequence of size n. They call that omega n, and it's conjectured that omega n is non-decreasing. Again, this would help with a lot of inductive proofs. When omega n plus 1 is bigger than n, when it's strictly increasing, then that sequence with the max tail is unique, and it's what they call an especially good starting sequence. So these are places where you might want to take a look. So they had proven everything up to roughly 36. So they looked at everything, all 36 long combinations of 2s and 3s, and they've identified the longest tails that were ever generated for those. And they conjectured out further to approximately 80. And so the question is, here's this curve, and what is the shape of this curve? Is it linear? Is it logarithmic? Is it exponential? I mean, it really is hard to identify with just 80 data points. There's our friend 2, 3, 2, 2, 2, 3, 2, 3. We just don't know anything about the shape of this. Now, maybe another way to take a look at this is to take a look at all 256 different ways of writing 2s and 3s and try to identify what their curl lengths look like or the tail lengths look like. You can see that there are only 3 tails that get very long at all. Most of them are below 10, and some approach 80. And in this case, there's a unique one, which is something like 78, I think. And, but it's interesting to see that these are extremely rare, these long tails, and that down below, there's sort of a fine structure, which is still not really yet understood. Here's the profile when we add one more character to it. It doesn't really add any more information. It's just sort of falling in under n equals 8. Here's what n equals 11. All of a sudden, there's a big jump, and what was 60 has now become 120 through the scaling of GNU plot. We see everything here, so we see all 2048 different sequences, and there's one that has a sequence length of, I think, 110, 112, something like that. And then for 13, we had to mention 13. So if you're going to go to get pizza tonight, I think 2, 3, 2, 2, 3, 2, 3, 2, 2, 2, 3, 2, 2 will keep you occupied for the slowest pizza joint you can find. Now, the power of the prefix. So we'd like to do inductive proofs by adding things on the front. So here what I've done is I've taken a 4-letter sequence, a 4-number sequence, 2333, and you can see that the tail is 341. If you add a 2 or a 3, it doesn't really do anything to it. Sometimes they change, so if you add a tail to, or if you add an extra digit to 2323, in the 3 case, it actually changes the contents of the tail, but the tail doesn't get any bigger or smaller. Some are active, and we see 222, in one case we see it gets longer, and in some cases it gets shorter. And the thing we worry about is if it gets too short, in both cases, then our inductive proofs would fail. So here's the sequences that Ben and Neil had found. Our big idea was to just explore all 563 trillion other sequences under n equals 48. This is a lot more work than he did. And like all teenage boys, they said, this is a dumb idea, and then we went ahead and did it. And so we added 14 more data points. None of them are doubly run. Well, it turned out that we could break our sequence down into a pattern of short sequences and long sequences. And that pattern is a aperiodic grammar, and it has some really cool L system properties. It has this sort of binary comb effect. You can sort of parse the sequence into parts, and we can now inflate, I have to hurry on through here, but we can actually take arbitrarily short sequences and inflate them into arbitrarily long sequences. So we know that they can get quite long, but our graphs of, one of the amazing observations is the curl operation is bidirectional, so there's no free will. If you sort of identify how many suffixes there are that repeat, it also is telling you how many prefixes of the remainder of the sequence will repeat, and that's kind of cool. So there's more things for me to tell you. I'd be happy to talk to you about any of this, and all of these plots are self-similar, so just take a look at any one of them. Yeah, the conclusions are basically we think that it's going to be a linear graph, and it still remains a very interesting problem to take a look at. Thank you.